In this video, we're going to look at solving stoichiometry problems, which are just quantitative chemical reaction problems based on mass measurements, where both reactants and products are measured in units of mass. We're also going to look at an example quantitative stoichiometry problem. All of these will be based on a basic balanced chemical equation, an example of which we have here. In this particular chemical equation, we see that 2 moles of sodium phosphate, reactant 1, reacts with 3 moles of magnesium chloride, and both of those are aqueous, meaning dissolved in water. And that gives us, when the reaction occurs, 1 mole of magnesium phosphate, and we know that this is a precipitate based on the solid here. And the other reactant, or product, is 6 moles of sodium chloride, which remains in solution. Now, each of these coefficients is a whole number ratio, and we understand that when there's no coefficient written there, that there's an understood 1. So 1 mole of magnesium phosphate on the product side is the understood coefficient there. Now we can take these coefficients and express them in ratios. So for example, we can take our 2 reactant ratios and take the mole ratios of those. We could take one of our products and express that as a mole ratio versus one of the reactants, and each of these will be simple whole numbers. So everything would be great if all the quantities were known in moles, but unfortunately in the laboratory, we don't measure moles directly. For pure compounds, typically solids, we would measure by mass, which would either be grams or milligrams. And for liquids, sometimes we might measure the pure compounds by mass, but more typically we would measure pure liquids as well as the solutions by volume in milliliters. So what we then need is to be able to use the information that comes from our basic balanced chemical equation, these mole ratios. We need to be able to convert first the information we have in whatever units we're provided from the laboratory, grams, milligrams, or milliliters, into moles. And then once we know the mole ratios and we get the mole information we want out the other side, then we need to convert that back into our laboratory measurement, grams, milligrams, or milliliters. So this particular video, we're going to make sure that all of our reactants and products are measured in grams. So this will be the simplest example of a stoichiometry problem. So let's stick with this particular chemical reaction. In this problem, we see that a solution containing 25 grams of sodium phosphate, so this reactant here, is mixed with a solution containing excess magnesium chloride. Now, magnesium chloride is our second reactant. When we see the word excess, that's a good clue. It tells us that we have plenty of magnesium chloride to react with all of that 25 grams of sodium phosphate. So all I need then is to determine what mass of the product, magnesium phosphate, I can produce based on the assumption that all of that 25 grams of sodium phosphate reacts. Now, if I had all my information in moles, it would be easy because I know from the ratios. So I have 1 mole, remember that's an understood coefficient of 1 out in front of the magnesium phosphate. I know that I can form 1 mole from every 2 moles of sodium phosphate. So in other words, I need 2 moles of sodium phosphate to form my 1 mole of magnesium phosphate. There's my 1:2 ratio. But since my information is not in moles, the first thing I need is to express my 25 grams in units of moles. And then once I determine how many moles of sodium phosphate I have, I can to translate that into moles of magnesium phosphate using the information from the chemical equation. And then last, I would translate that information back into mass. So I have a 3-step conversion factor problem: mass to moles, moles of reactant to moles of product, and then moles of that product into mass. The conversion to go from mass to moles is molar mass. So I know I need to know the molar mass of sodium phosphate to make that first conversion. And at the end, I need a molar mass again. I need the molar mass of magnesium phosphate to make that final conversion. So the first thing we'll do is to develop those molar mass tools. Okay, so let's see how we would get those molar masses. The first one I'm going to calculate is the molar mass for sodium phosphate, Na3PO4. There's 3 atoms of sodium, 1 of phosphorus, and 4 of oxygen. So I'll multiply the number of sodium atoms, 3 times the molar mass of sodium for the periodic table. Phosphorus 1, again, times molar mass from the periodic table. 4 for oxygen times molar mass from the periodic table. And I find I have 163.940 grams in each mole of sodium phosphate. Now the meaning of that is exactly that, 163.940 grams of sodium phosphate equals 1 mole. And so then I can, based on this equality, create 2 possible conversion factor ratios. I can put grams over moles or moles over grams. So when it comes time for me to do a conversion between mass and moles, I want to select the appropriate one of those 2 conversion factors. We'll do the same thing developing the molar mass for magnesium phosphate. There's 3 atoms of magnesium. Now, since I have 2 phosphorus groups, phosphate groups, there's 2 atoms of phosphorus. And since I have 4 atoms of phosphorus in each phosphate group times 2, there will be 8 atoms of oxygen in this particular molecule. So once I do all of that, I find there's 262.855 grams is equal to 1 mole of magnesium phosphate. And once again, I can make 2 possible conversion factors. I can put mass over moles or moles over grams. And again, whichever conversion I want will dictate which of the 2 conversion factors I pick. So let's go back to our problem that we were looking at and work through our conversion factors. Now, the way we'll lay out the problem is what we're going to call a chicken wire approach. That's where we're going to start with our beginning information, and the horizontal line will represent the line in a fraction, meaning numerator on top, denominator on the bottom. Each of those vertical lines is meant to denote a multiplication sign. So I'll take my 25 grams of sodium phosphate. The first thing I want to do is convert that to moles. So I want to cancel grams and keep moles. So I'll put grams on the bottom, moles on the top. My grams will cancel. Then, now that I know the moles of sodium phosphate, I'm going to use the information from the chemical equation, remembering there's an understood 1 out in front of magnesium phosphate. So I know that I need 2 moles of sodium phosphate to form 1 mole of magnesium phosphate. So that ratio comes from our stoichiometric coefficients. I want to cancel moles of sodium phosphate, so that goes in the bottom. There's my 2 moles of sodium phosphate, the 2 coming from here. The 1 mole of magnesium phosphate on the top, coming from there. My moles of sodium phosphate cancel. And at this point, then, I know how many moles of magnesium phosphate I can form. The last step, then, is to convert that number of moles into grams. To do that, I want to cancel grams and keep moles. So I'll put the moles on the bottom, the grams on the top, using this molar mass of magnesium phosphate. The moles cancels moles. And once I'm done with all of that, I can go through my multiplication. So along the top, 25 times 1 times 1 times 262.855, and then divide by 163.94, divide by 2, and then divide by 1. When I do all of that, I get a final answer, 20.0 grams. I want to express that in 3 significant figures because my starting information was also 3 sig figs. So that's how to do a stoichiometric problem, starting with a basic balanced equation where all of the reactants and products you're interested in are expressed in laboratory measurements of grams.